the thing that makes this difficult is all of the different masses and numbers and things. You end up with millions and millions of variables, and you've got to be clear about which is which is which. Okay, so we've got an insulated copper can, so that's this thing. It's got a mass of 20 grams and it contains 50 grams of water, so it actually, that's labelled. They're both at a temperature of 84. That is also labelled. We've got a block of copper that's got a mass of 47 and a temperature of 990. Yeah. And it's lowered, so it's really hot. And it's lowered into the water as shown in the figure below. So it ends up in the water. As a result, the temperature of the can and the content, so we've now got two different materials are warming up, reaches 100 degrees. So the can gets to 100 and some of the water turns to steam. So what if we actually got going on? Right, it says calculate how much thermal energy is transferred from the copper block as it cools to 100. So it's saying to do this first, and then if we move on, it then says calculate how much of this thermal energy is available to make steam. Okay, and it says assume no heat is lost to surroundings. So we're going to do it in two steps then. So let me clear all my drawings a minute. So we want to, first of all, calculate how much thermal energy is transferred from the copper block. So which of our equations, Q is equal to mc delta T or Q is equal to ml, are we going to use for our copper block? The first one, good, because its temperature is changing. Okay, so Q is my thermal heat energy, right? Is the mass of the copper block. Okay, so it's M for the copper, C for the copper, delta T for the copper. Right, now mass for the copper is 47 grams. It's times 10 to the minus 3. The specific heat capacity for the copper is there. That's 390. And the temperature change is, what's our temperature change? Our starting temperature is 990 minus our ending temperature is what? 100. Okay, so you're right, so it's 890. Now technically we should have put the 100 first because that's the final temperature, and our Q value should be negative because it's energy lost. But and this is one of the complications, again, it's all about freaking negative numbers. Okay, if you choose to think about positive numbers and always put the big number first and the little number second when you're dealing with a temperature change, then you can think about whether the heat is going in or out, and you can make it positive or negative according to your logic. So I am going to put the big number first and the little number second. If you prefer to do it the other way, you can. You just have to be consistent. So if we actually do this, what do we get? 47 times 10 to the minus 3 times 390 times 990 minus 100 gives me a silly number. Right, I get 16.3 kilojoules times 10 to the 3 joules. Okay, that is the heat lost by the copper bar. Okay, right, what's the correct number of significant figures? Because it just so happens to say an appropriate number of significant figures. So Andina is correct, it's 2. Everything is to 2. So my answer's not right. I should have done 16 times 10 to the 3, so 16 kilojoules. Okay, so Q is actually 16 kilojoules. Two significant figures. Right, okay, so we've done part I. Right, then let's zip up a minute. What's part I? It says calculate how much of this thermal energy is available to make steam. So now what we've got to do is we've got to think about what's going on. When heat is lost by the copper, what does that copper bar provide heat for? Well, we're going to warm up. The copper's losing energy, so that energy has to go somewhere. It's heating the water and it's heating something else, the can, and it's also turning some water into steam. Now you're right, in the real world, Krishiv, it will be heating the surroundings. But in this example, we are told that it doesn't lose any energy to its surroundings. Where does it say it? I read it, I can't remember. There it goes. Assume no heat is lost to the surroundings. It says assume that no heat is lost. So yes, in the real world, you would obviously be losing heat to the surroundings. But in this imaginary A-level physics world, we don't lose heat to the surroundings. Remember, keep it simple, stupid. Yeah, the KISS thing, right? So you're too clever. So you've got to kind of dumb it down. We're going to not lose any heat. So now I'm going to write an expression now, which will allow me to figure out what is happening with the heat. So the heat that we are using to heat up our can and our water and to turn our water into steam, three things, we are getting from our copper. So the heat lost by the copper is providing three different things. It's heating up the can. So this is the heat gained by the can. Gained by can, right? We're also heating up the water. So this is Q for the water. So this is gained by the water. And all of the water gets to 100 degrees because it boils. We're told that it gets to 100 degrees, but some of the water turns into steam. So we also have, I'm going to call it QS. This Q is turns water to steam. Can you see how complicated this is? And we haven't even got any melting ice cubes. So now what we've got to do is we've got to work out QS. That is what they've asked us to work out. So you can see that QS, let's write it down here, is equal to Q copper minus Q can minus Q water. That's what we've got to work out. So we've got Q copper. It's 16 kilojoules, so 16 times 10 to the 3 minus, right, now what's Q can? Right, the can is just changing temperature. So we're going to use this equation for the can. And if I go back, what we know it's 20 grams and it's made from copper and it's at 84 degrees. Da, da, da. Right, so we can do M for the can, C for copper, and then our temperature change is delta T for the can. And our QW is mass for the water times the specific heat capacity for the water times the temperature change for the water. Okay, so the mass for the can was 20 grams times 10 to the minus 3. Specific heat capacity for copper was 390. What is my temperature change for the can? Can you remember? It was
84 to 100, wasn't it?
Yeah, it was at 84 degrees. It's going to get as hot as the water, but no hotter. Okay. Well, of course, in the real world, it probably would get a bit hotter because, especially if the copper bar is actually allowed to lie on the bottom. So, yeah, again, it's not nice. So, what we're going to do then is we're going to say that it is let's make it positive because I need this number to be negative. So we've got to have our bigger number first. Can you see how you need to be careful about your positives and negatives? So I'm going to put my bigger number first, 100 minus the 84. Okay. So, and in fact, that is the final number minus the initial number, right? And then we're going to take away, right, the mass of the water. I can't remember how much water there was. Was it 50 grams? Yeah, 50 grams of water. So we've got 50 times 10 to the minus 3 times 4,200 times, and the temperature change for the water again is 100 minus 84. That is the sum we've got to do. Can you see how complicated it is? You have to be really clear about what's going on. So constructing this equation is your key. Okay, right. For 2 marks. Yeah, I know. Isn't it horrible? Yeah, the trouble is, my love, we don't know what M is for E is ML. Well, Q for copper technically isn't negative, but the Q that's lost by the copper is given to all of these numbers, and all of those numbers positives. Can you see it's on the other side of the equation? So we can make them equal to each other. The heat lost by the copper, Dina, is the heat gained by the can, the water, and the steam. So we can make them equal to each other. Oh, yeah, she says. Yes, the positives and negatives make it hard. It really, really does. Right now, I can't be bothered to do all of those sums, but it's not difficult. Once you've got Q for the steam, and obviously I haven't done it, but once you've got Q for the steam, I'm going to delete all this. Once you've got Q for the steam, that you're calculating there, you can do Q for the steam is equal to mass times the latent heat. So you can get M is equal to Q over L, whatever your Q is for the steam divided by, and the latent heat for steam is an enormous number, 2.3 times 10 to the 6. So we end up with we end up dividing it by 2.3 times 10 to the 6, and you'll get some number of grams. This is the mass of the steam, which should be less than the 50 grams of water. Okay, can you see how difficult these heat questions are? You have to include everything. In this particular one, the thing that makes it hard is the fact that there's a can there. Okay, so it's an extra thing. So we've got things changing temperature and things changing state. So we've got water turning to steam. If what you're doing is dropping in ice cubes, of course the ice cubes turn into water, but they turn into water at 0 degrees. So you then have to warm them up to the final temperature. And so you need to be really clear about which things are warming up and which things are cooling down in order to work out what your final temperature is when you're dealing with ice cubes.